A uniformly charged sphere in a cylinder. A uniformly charged insulating sphere with radius r and charge plus capital Q lies at the center of a thin-walled hollow cylinder with radius capital R greater than r and length capital L greater than 2r. The cylinder is non-conducting and carries no net charge. Okay, so we have a cylinder which is insulating with no charge. We have a uniformly charged insulating sphere inside this cylinder. Part A, determine the outward electric flux through the rounded side of the cylinder, excluding the circular end caps. Hint, choose a cylindrical coordinate system with the axis of the cylinder as its z-axis and the center of the charged sphere as its origin. Note that an area element on the cylinder has magnitude dA equals 2 pi r, capital R dz. Okay, so in this video we will be worrying about this part of the problem. So we have a cylinder, a non-conducting cylinder with no charge on it. We have a uniformly charged sphere inside. So here is our coordinate system, x-axis, y-axis coming out. So let's see here. So this has to be y-axis going in, right? So to make it right-handed coordinate system, I hat cross j hat should be equal to k hat. All right, so the z-axis is the vertical axis here. So if I look at the side, the rounded side of the cylinder, and I look at an area element here, so this has thickness, you can see here this thickness is dz. Now it has a radius capital R, so 2 pi capital R times dz is really the area of this element. So it is 2 pi capital R times dz. Now this uniformly charged sphere inside will create an electric field on this rounded side. So let's say that this electric field is making an angle theta with respect to the horizontal axis, the x-axis here. And this area element is located at point Z. So this is basically point Z on the z-axis. And tangent of this angle theta, so basically this is perpendicular. So you can see that tangent of this angle theta is Z divided by capital R. All right, so we have tangent theta is equal to Z divided by capital R. What about cosine theta? Cosine theta will be this side r divided by the hypotenuse. So what is the hypotenuse here? If this is z, this is capital R. The hypotenuse will be z square plus capital R square square root. So cosine theta will be equal to capital R divided by z square plus capital R square square root. And why do I need cosine theta? Because I want to calculate the electric flux. So I need the perpendicular component of the electric field, which will be E cosine theta. E sine theta is basically perpendicular to the area vector on the side of the cylinder. So it's not going to count for the flux calculation. So what is the flux d phi E on this area element? It is basically E cosine theta, the component of the electric field, which is parallel to the area vector, multiplied by dA, because the area vector is pointing in this direction, electric field component is in the same direction, so the dot product gives me the product of the magnitudes. So this basically is equal to the electric field E cosine theta multiplied with 2 pi capital R dz. So I have 2 pi capital R multiplied with R, so that gives me 2 pi capital R squared dz divided by z square plus capital R square square root. All right. So now I need to know what this electric field is. So basically we have to find the electric field outside a uniformly charged sphere. This is the sphere at the center, which is creating this electric field at this point. Okay, so in order to do this calculation, we take a Gaussian surface, a spherical surface with radius r prime greater than r, the radius of this sphere. So this sphere carries a total charge q, and the electric field lines are pointing radially outward. Now, writing Gauss law, the closed surface integral E dot dA, the net flux through this Gaussian surface, is equal to the charge enclosed by this surface divided by permittivity of free space. Now, what is the area of this sphere? It is 4 pi r prime squared. Because the area vector is also pointing radially outward, I have E dot dA equals E dA, which is E times 4 pi r prime squared. The electric field magnitude is constant on this surface because it's only a function of r prime. So this is equal to the charge enclosed. What is the charge enclosed? The charge enclosed is the total charge carried by this sphere, which is Q. So capital Q divided by epsilon 0 in Gauss law. And this gives me the electric field magnitude at r is equal to r prime to be a 1 over 4 pi epsilon 0, which is Coulomb's constant K, total charge capital Q divided by r prime squared. Okay, so what is r prime? The distance between the center and the radial distance from the center of the sphere to the point of interest where we're trying to calculate the electric field. So going back to my original figure here, that distance is this distance, which is square root of z square plus capital R square. So that's this total distance here. All right, so that's including R. So let's basically make sure that we don't confuse that with capital R. So this total distance here, is basically z square plus r square square root. All right. So we note that here in our calculation, the radial distance from the center is r prime, which is r prime square is equal to z square plus capital R square. So for the electric field at that point, magnitude, I should write K capital Q divided by z square plus capital R square. Then I can substitute this result to my flux expression. for d phi e. So that gives me then for d phi e, I have the electric field kq over z square plus r square multiplied with this. So z square plus r square multiplied with square root of z square plus r square, I will have z square plus r square to the power 3 over 2 at the bottom. So here I will have z square plus capital R square to the power 3 over 2 at the bottom. And then I have kq coming from the electric field magnitude. And then I have 2 pi capital R square dz. So I have to put that here. 2 pi capital R square dz. All right. So that's the flux, electric flux on this side surface, which has area 2 pi r, 2 pi capital R dz. Now, in order to find the total electric flux through the side surface, I have to integrate from z is equal to minus L over 2 to plus L over 2. Consider all such surfaces, the contributions, because the flux is always in the same direction parallel to the area vector. The result is just an integration. So phi e, the total flux, will be equal to things that don't belong to this integral can be taken out. K capital Q 2 pi capital R square integral from z is equal to minus L over 2 to plus L over 2. Then I have dz divided by z square plus r capital R square to the power 3 over 2. Then I have tangent theta is equal to z divided by capital R, and capital R secant square theta d theta is equal to dz. So if I differentiate both sides, so in other words, I'm substituting z is equal to capital R tangent theta. And what is z square plus r square then? It's going to be r square parentheses 1 plus tangent square theta. And I know that 1 plus tangent square theta, trigonometric identity, is secant square theta. So this is basically all the information I gather from this triangle here. Tangent theta is z over r, and I'm using this substitution in order to solve this integral. So if I take this triangle here, just to be clear, I have this angle theta. This is a right triangle. This is z. This is r. And this is z square plus capital R square square root. So that all comes from this triangle. All right. So if I make this substitution to my integral here, I'm going to obtain k capital Q 2 pi capital R square. This will be integrated from theta minimum to theta maximum. For dz, I'm substituting capital R secant square theta d theta. So this is capital R secant square theta d theta. For z square plus r square, I'm substituting capital R square secant square theta. So this is going to give me capital R square secant square theta, that is z squared plus r squared. So this is secant squared. This is to the power 3 over 2. So here I obtain k capital Q 2 pi capital R square integral from theta minimum to theta maximum. On top I have capital R secant square theta d theta. At the bottom I have capital R cube secant cube theta, because this 1/2 gets rid of the squares. All right. Now you can see that this capital R and this capital R square will get rid of this capital R cube. All right. And I will be left with secant square divided by secant cube, which is going to get rid of this cube, and there's only one secant remaining here. So d theta over secant theta, which is cosine theta. So this is going to give me k capital Q 2 pi integral from theta minimum to theta maximum, which I haven't determined, cosine theta d theta. And what is the integral of cosine? That is sine. So k capital Q 2 pi sine theta evaluated between theta minimum and theta maximum. And what is sine theta? I can determine here. It is z divided by square root of z squared plus r squared. So if I substitute that for sine theta here, this is k capital Q 2 pi z divided by z squared plus r squared square root, the hypotenuse. And here z varies between minus L over 2 to plus L over 2. All right. Now I can substitute plus L over 2 and minus L over 2. So if you substitute plus L over 2, this is L over 2 squared plus R squared. If you substitute minus L over 2, that's minus L over 2. Again, L over 2 parentheses squared plus R squared. The denominator will be the same. There's just going to be a minus sign because I'm subtracting the evaluation at the minimum value from the maximum value. This is going to give me the following answer. For the flux by E, I have K capital Q 2 pi L over 2 L squared over 4 plus capital R square square root. Then I would evaluate it at minus L over 2 and subtract this. So that just implies that I'm multiplying this by 2. So this gives me K capital Q 2 pi capital L. And now this is L squared plus 4R squared over square root 4. So that's basically coming on top as multiplication by 2. L squared plus 4R squared square root. So this 2 comes from this 4 here. L squared plus 4R squared divided by square root of 4. That is basically 2. So I get my final answer when I substitute for K 1 over 4 pi epsilon 0. The total flux phi E is Q times L Q times L divided by epsilon 0, because it is 4 pi here. So it's 4 pi epsilon 0, 1 over 4 pi epsilon 0, and 4 pi cancel. And I have capital L square plus 4r square square root. So this is my final answer for the flux through this rounded side of the cylinder. Okay, so in this problem we have a uniformly charged sphere in a cylinder. The cylinder is non-conducting and carries no net charge. In part A, we want to know the outward electric flux through the rounded side of the cylinder. We want to exclude the circular end caps. And to do that, we're considering area elements with area 2 pi r dz. So this is the x-axis, this is the y-axis going into the page, and z-axis is the vertical axis. And at a location z on the z-axis, we have an area element 2 pi r, 2 pi capital R dz. And the electric field at that point has a component E cosine theta, which is parallel to the area vector, which is the radially outward vector. So the flux is E cosine theta times dA. And in order to find the angle here, cosine theta, in terms of z, we can look at this right triangle. Cosine theta is capital R divided by square root of z square plus r square. So E multiplied with dA, which is 2 pi r dz, the circumference multiplied by the height. So that gives me, with this r, 2 pi capital R squared dz divided by square root of z squared plus r squared. The next task is to calculate the electric field created by this uniformly charged sphere at this point. To do that, we'll take a Gaussian surface, spherical surface, use Gauss law in closed surface integral E dot dA, which is E times 4 pi r prime square, which is the surface area of the sphere, is the charge enclosed, which is Q divided by epsilon 0. So we find that the electric field is KQ over r prime square, where r prime is the radial distance from the center of the sphere to the point where we want to know the electric field outside of the sphere. So it is square root of z square plus capital R square. So it is kq over z square plus capital R square. So d phi e is the integral of this between z equals minus L over 2 and plus L over 2. With the z equals capital R tangent theta substitution, we can easily solve this integral and evaluate it between these limits, minus L over 2 and plus L over 2. And this gives us our final result, capital QL over epsilon 0 square root of L square plus 4R square, where we have substituted for Coulomb's constant K, 1 over 4 pi epsilon 0. So in the next video, we will worry about part B of the problem, which has to do with the electric flux through the end caps.